Hi, everyone. My name is Prashant, and as Sasha mentioned, I'm from the 3D graphics lab in Concordia University, and I'm a PhD candidate here right now. So I will be talking about a bit about our work on sharp feature detection in point clouds. First, I'll be talking about why sharp feature detection is important, and we'll do a little detour talking about deep learning and point clouds because there's been some really interesting developments in the past year. And after that, I will shamelessly plug our lab's work on sharp feature detection and its applications. First of all, a really simple question. What is a sharp feature? A sharp feature mathematically is a discontinuity in the normal field of a surface. So for example, you can see that over here, the normals are kind of discontinuous at the sharp edge over there. Now, sharp features are usually the easiest thing to lose when you're actually scanning something or capturing 3D data through other methods. And that's because they're high frequency data, so it's really easy to lose them when there's a little bit of noise or something. And when you reconstruct them, you could easily lose them again because when you smooth stuff, you also smooth out the sharp features along with the noise. And why is it important to preserve these sharp features? One really obvious one, which people in image processing will probably be familiar with, is it provides edges and other features for downstream computer vision algorithms. And another more CAD-related application is that if you can detect the sharp features on a scanned CAD object, you can probably reverse engineer the CAD model and make modifications to it yourself. And there's also the very obvious application, which is just making the object look better or more accurate. And I'm sure that this being Autodesk, people over here can think of even more applications for it. So at what stage of the reconstruction process is it a good idea to reconstruct these sharp features? Do we do it when we have a mesh? Well, it depends on how good the mesh is. Of course, if we have a mesh, there's a really easy way to detect sharp edges, which is you just look at the angle of the two faces on either side of the edge, and that's it. Just set a threshold for that. But that could actually be too late in the process to actually improve the quality of the 3D data. So it's often a good idea to work on the point clouds themselves. And once you're done with the point clouds, then try to make a mesh out of it. But of course, this is more challenging because there's less geometric information. So I'm going to talk a little bit about a particularly interesting development in deep learning, which is from last year, which is called Pointnet. And it's basically a neural network for classification and segmentation of point clouds. And the really exciting thing about Pointnet is that you can give raw points directly to a neural network. That's something which we hadn't really seen before last year. And I think Mike had already covered some of the other Pointnet-related papers. But this is another one I find really interesting, which is the generative models based on Pointnet, where you can use Pointnet-based autoencoders to generate new point clouds. And let me just describe in a really simple way the idea behind Pointnet. And let's start really simple. Can you give a simple, fully connected neural network a set of, say, 1,000 3D points, and then use that to classify the point set? Well, the answer is yeah, kind of. It's kind of counterintuitive. But of course, you need a few modifications to the network in order to make this possible. And with this sort of architecture, you get 87% accuracy for classification. So the secret behind Pointnet is, first of all, you need some one-by-one convolutions in order to share the weights between the points that the network receives as well as their x, y, and z coordinates. And you also have a max operation at the end of a bunch of layers, which makes the neural network permutation invariant. So the first half of the network will actually give you the same result regardless of the permutation of the points you give it. And the actual Pointnet, which is like the final version of it, is a little bit more complicated because it has a couple of spatial transformer networks inside it. And the spatial transformer network is kind of like a network inside a network, so you can backprop while you backprop. And it's also used for segmentation as well. And what does this added complexity give us? 89% accuracy, which doesn't sound like a lot, but it's actually, I mean, it's once your accuracy is pretty high, it's a lot harder to get small improvements in it. So just to summarize the idea behind Pointnet, you start off with thinking of fully connected layers, and then with shared weights and having a max operation, you make it permutation invariant. And at the end, you have a transformer network which improves the results a little bit. Now, of course, we started by talking about sharp features. Can we use Pointnet for detecting sharp features? Well, first, let's see how well Pointnet does for an experiment which the authors themselves tried, which you can find in the appendices of the paper, which is normal estimation. And what the authors found is that the normals they estimated for point clouds were smoother than ground truth. That doesn't sound too encouraging. So what about sharp features? Supposing we have a model like this with the sharp features marked on it. Can PointNet-based models learn to mark these sharp features on it? And let's say, for example, that we give it a particular neighborhood and use the features provided by PointNet to try and mark these sharp features. It turns out it's not that easy. It has a hard time even memorizing the training data set. So we tried using transfer learning, training it from scratch, as well as training an autoencoder and using the encoder as the first half of another neural network. Although it is interesting to note that it does a good job of identifying corners. Because what PointNet actually does is it kind of learns to detect landmarks in the point cloud. So perhaps that's why it does a better job of detecting corners. So here are some of the limitations of PointNet. The first is actually a limitation of neural networks in general, which is that PointNet has a fixed number of points. So if you train it to, say, classify point clouds with 1,000 points, that's it. You can only use it for point clouds with 1,000 points. And the next one is not such a serious limitation, which is it expects a scale similar to what it has seen in the training data. But it's not that difficult to actually change the scale of your data to make it fit with that. And it implicitly learns to detect landmarks, which is good for classification and segmentation. It's not so easy to use that for estimating local geometric properties, though. So this is our lab's upcoming paper, where we not only use neural network to detect sharp features, but we also apply it to feature-aware smoothing of a point cloud. So the idea behind this is we define something called a proxy surface. And by uniformly sampling a fixed number of points on a geodesic disk, that takes care of a bunch of the limitations of neural networks. First of all, the fixed number of inputs. And you can easily scale or normalize the thing by the size of the geodesic disk. And you also get a grid structure, which is great for convolutional neural networks. And the way we do it is by using an interpolation technique called moving least squares to interpolate the neighborhood of the point cloud. And in case anyone is wondering why I appear to be showing you a mesh, that is just for visualization. We're actually operating only on the points. This is an example of like a feature you could define on this geodesic disk, the point sample on it, like the angle between the normals at those points and the central normal. And you will notice that if you arrange these angles, they actually form particular patterns which depend on whether you're at a corner or an edge or a smooth area. And at this point, we've essentially reduced this geometry problem to an image processing problem, which is great for convolutional neural networks. So we just train our CNN on this type of data using some simple synthetic models. And it learns to actually generalize to more complicated shapes. These are our results, not training data. And we have a CAD shape, we have a 3D scan of a CAD shape which somebody else made, and our 3D scan of an object in our lab. And it's pretty robust to noise. It's still able to detect these sharp features. And I can quickly run through some applications of this. One obvious application is segmentation. We can segment these objects into patches based on the detected edges. And that is, of course, useful for reverse engineering a CAD model. And feature-aware smoothing. So we can take a noisy point cloud like this and modify moving least square smoothing in order to get sharper looking edges. And the way we modify it, for those who are familiar with moving least square smoothing, we basically take the usual Gaussian kernel and make it anisotropic so that it stops at the sharp edge. And here are some more of our smoothing results. You'll see that these ones at the bottom, the edges kind of look like they're chiseled out of stone, really sharp. And so to conclude, there's plenty of scope for research in combining 3D geometry and deep learning. I think that we're going to see a lot more exciting developments in the coming years. And you can actually take a look on a lot of more work on meshes on this site, geometricdeeplearning.com. I didn't have time to cover that in my talk. And it's not over for Pointnet-based approaches because it turns out last week some code was released specifically for detecting geometric features using a Pointnet-based architecture. So I'm pretty excited to check it out. It's called PCPNet, and I encourage you to as well. So I hope this was interesting for you guys.
Thank you, Prashant.